welcome Professor Prateek Sharma of IISc to the last of the special colloquium of the VSM special colloquium that have been organized to mark 1 year of regular weekly VSM meetings at RRI. Prateek, it's a particularly a pleasure for me because he's also a collaborator. We have worked together for a number of years now. And Prateek did his PhD from University of Princeton, and then he spent some time in Berkeley as Einstein Chandra Fellow, which is a prestigious fellowship. And after that, he has joined IISc. Prateek has made a significant contribution to the understanding of multi-phase structure of the intercluster medium, among other things. And he has recently extended these same ideas to the understanding of the galactic medium. And I think Prateek is going to talk about that today. So, Prateek.
Okay, thank you, Viman, for the introduction. So I'll start sharing the slides. Hopefully everything will be fine. So I'm starting. And I'll use the pointer. Okay, so can you see the slides?
Yes.
Okay, so you know the whole screen is visible, right?
Yeah.
Okay, so I'll be talking about the circumgalactic medium as seen through idealized models. So the background picture here is like an artist impression of the circumgalactic medium, the topic of my talk. And the circumgalactic medium is the diffuse medium surrounding galaxies like our Milky Way. So there are things falling in like these blue streams here in the artist impression, and material thrown out in form of galactic outflows marked here in red, and also some gas which is sort of neither falling in or blown out. So you know, just to set the scale, the size of this whole thing, the circumgalactic medium, is of order the size of the dark matter halo which hosts the galaxy, like our Milky Way. So when I talk about CGM, I'll have Milky Way in mind, but you know, it sort of covers a significant range below that or above that. We are talking about isolated Milky Way type galaxies rather than ones which are affected by being in a cluster or in a group. Okay, and so the scale of the CGM, the global scale of the CGM is around 300 kpc, whereas the scale of the disk is about tens of kpc. So you know the CGM is much bigger than the ISM and the stars in the galaxy. Okay, so here is the outline of my talk. So I'll be talking about the two approaches for doing galaxy formation through numerical simulations. One is the top-down approach, which is the most common and popular approach, which is to use cosmological simulations to study galaxy formation. The other approach is that of idealized simulations, which I call the bottom-up approach, which is much more simplified, but also I'll argue quite powerful to study galaxy formation. Now, one of the focus is why study the CGM if you want to understand galaxy formation, and the reason for this is quite simple. The CGM has an overdensity of order 10, of order 100 to 10.
Prateek, sorry to interrupt.
Yes.
Sorry, Ashwin here. Have you changed the slides by any chance?
Yes, I have changed my slides.
We have not been able to, see the switch in the slides. There may be an issue.
Next for sharing is paused. Bring your shared window to the front. This is my shared window. Is it changed now?
No.
Oops. This is saying bring your shared window to the front. Okay, let me actually stop sharing and start sharing again. Thanks.
Yeah, now you can see. And now you can see the outline.
Yeah, but I want to be in the slideshow mode. So let me share the desktop. Let me stop sharing and come back with sharing. Yeah, thanks for reminding, Ashwin. I would have just talked like that. Okay. Share screen, desktop, share. Okay. Spotlight. Okay, can you see my
Yes.
second slide now?
Yes.
Okay, good. So this was the outline. Thanks, Ashwin, again. Oops.
Yeah.
Where did my pointer go? Okay, just a sec. Annotate. Spotlight. Okay. Okay, here I was. And you can see my full screen, right? Hello?
Yes. Yes.
Okay. So, I'll be talking about the top-down and bottom-up approaches to doing galaxy formation via simulations. And, then I'll talk about why we want to study the CGM if we want to understand galaxy formation, rather than focusing on stars, which we traditionally do. And the fundamental reason for that is CGM, although nonlinear, is still linear compared to star formation. Stars have a density which is very, very high compared to the density compared to the average density of the universe. So, stars are much more nonlinear compared to the circumgalactic medium. So the reason most of galaxy formation was equated to understanding stars was because we could not observe the CGM earlier, because we did not have observational capabilities. But now we have several probes which can observationally probe the CGM. So I'll argue that the CGM, if we can understand the CGM, we can better understand galaxy formation. The key question that I'll be focusing on, why, I'll show observations which show that the circumgalactic medium is multi-phase. And the key question is, how do you explain it? And by multi-phase, I mean you see gas at several different temperatures, ranging from 10 to the 4 Kelvin to the hot X-ray emitting plasma. So the gas exists at different temperatures, perhaps in rough pressure equilibrium between these different temperature phases. I'll talk about some idealized models, and I will focus on this cloud crushing simulations, which we recently completed, and hopefully this paper will be out on archive in a day or two. It was supposed to come out today, but somehow they put it on hold. I don't know why. I was really not very happy with that. Okay. So the first part is galaxy formation simulations, ranging from cosmological hydrodynamic simulations. So these are very realistic, but the problem is they have a lot of knobs and free parameters that have to be adjusted to give you answers which match observations. The second extreme is idealized setups, where you strip down most of the elements and focus on the most important things. And this is, of course, your judgment. These are not as realistic, of course, as the cosmological hydrodynamic simulations, but here we can study the processes in great detail. So the best way is to actually combine these two approaches, understanding the underlying physics here and running these simulations and interpreting them from the results of the idealized simulation. So that's the most fruitful approach. Now this is the sort of example of top-down approach to galaxy formation. For some reason, my text is hidden behind the images. This is not good. Let me actually, give me a second. Huh? This was not like this. Okay, I think this was the only slide. Perhaps there was a problem. Sorry. So I'll do the slideshow again. Sorry about that. Okay. So this is the state. One of the state of the art galaxy formations. You can see my slides, right? The illustrious TNG snapshots you can see. Okay.
Yeah.
This is sort of an example of this top-down approach to galaxy formation that I was talking about. What you see here are cosmological hydrodynamic simulations of galaxy formation. And this is from the TNG group, the next generation of illustrious simulations. So, you know, the TNG 300 has a box size of 300 megaparsec, TNG 100 is a 100 megaparsec box size, and TNG 50 is 50 megaparsec. So they are all pretty big volumes, and they include a lot of physics like self-gravity, n-body dynamics of dark matter, cosmological background, you know, background expansion, hydrodynamics, prescription for star formation, initial mass function, prescription for black hole growth, cooling of the gas at different temperatures, which ranges from hot in emitting X-rays to molecular gas, feedback, you know, very detailed feedback models due to stars and black holes. And this is all done at as high a resolution as possible. But even for the state-of-the-art cosmological large volume simulations, you cannot get resolution better than 100 parsec. So this 100 parsec is a ballpark number for TNG 50, right? So this is one of the highest resolution simulations, because the reason for that is you're simulating a very, very big box, which is 50 megaparsecs. So scale separation between 100 parsec and 50 megaparsec is still enormous. So here, so there was a recent review by Vogelsberger et al. On different galaxy formation simulations, and you know, these are hydrodynamic galaxy formation simulations, and you know, there are different types. So this is sort of like a landscape of galaxy formation simulations. So these two are dark matter only simulations. These were very popular like 20 years ago. So where you only simulate the dark matter, self-gravity of the dark matter, and simulate structure formation in the universe, but do not evolve hydrodynamics of the gas. So the most popular of these was this Millennium simulation. The movies and images of it, most of you may have seen. So these are dark matter only simulations. But since these are only dark matter simulations, how do you infer properties of the galaxies that form within these halos? So for that, you need something called semi-analytic models, or SAMs. So these are physical prescription used to color these dark matter simulations to produce observational properties like galaxy colors and galaxy masses and so on. So the right column here shows the recent development and these large volume cosmological hydrodynamic simulations. So this is like illustrious TNG and so on. So they are still doing very big volume of order hundreds of megaparsec, right? So these are large volume cosmological simulations. So, you know, illustrious TNG, Eagle, you may have heard some of these names. And then there are some things called cosmological zooms, where you don't simulate as big a volume as these cosmological simulations, but you know, you put a lot of resolution in the region where you expect a galaxy to form. So the outer parts are not well resolved, and all your resolution elements are on a single halo. So this here you can achieve more resolution than here, but here you don't get a lot of statistics. So this is the landscape of cosmological galaxy formation simulations. What about this bottom-up approach, which I argue is also very, very powerful? In this approach, you only include the most important. Of course, this most important is a subjective choice processes. And for example, if you want to simulate the intracluster medium, you can have a fixed dark matter gravity. You can have a simple prescription for feedback from AGN. And in such simple setups, you can ask very pointed questions like, what is the resolution requirement for convergence? When is it that you suspect your results to be affected by numerics and so on? And here you can actually also do, you know, variations like 1D, 2D, and do large parameter variation, because these are typically much faster than those cosmological hydrodynamic simulations. So, for example, I recall like this illustrious TNG 50 simulation was running for almost a year in one of the biggest supercomputers in Germany. Now, so these are much faster because they're not as ambitious, but they are also very powerful because you can study emergent phenomena like you know, you can study things like, are there any emergent physical principles which govern the appearance, at least the coarse-grained appearance of the circumgalactic medium and the intracluster medium. So I'll actually briefly touch upon these important ratios, this ratio of cooling time to the free fall time, and the ratio of cooling time of the mixed gas to the cloud crushing time later. Now, this approach is actually, inspired by, these two quotations here. So, everything should be made as simple as possible, but not simpler. So the idea is, you want to strip down most of the complications, but not the essence of the problem. So my claim is that we do capture most of the important, the most fundamental processes, but not everything. And similarly, the quotation by Niels Bohr is also very pertinent. So it says the opposite of a fact is a falsehood, but the opposite of one profound truth may very well be another profound truth. So in this context, I interpret this as that, these very heavy duty cosmological galaxy formation simulations are very powerful. That's a profound truth. But this is an opposite statement, which is you can have very, very simple idealized simulations of galaxy formation, and yet this is also very powerful. So this is opposite of that, and yet the truth. So, I sort of like this statement. So it's not obvious. In this context, I thought that it was pertinent. So why idealized models? I mean, the whole of physics is based on idealized models. Here, everyone, all of us have studied simple harmonic motion and Hooke's law for springs and, massless threads and pulley, frictionless pulleys. So all these are examples of idealized models. None of the real things that we deal with have, are so simple, and yet studying these models in great detail help us understand the real complicated things much better. I mean, the same goes for things like continuum hypothesis. We know that matter is composed of atoms at small scales, and yet we use hydrodynamics, Navier-Stokes equations, which is, of course, wrong if you think it in a naive way, but it's very, very powerful. Similarly, we apply ideas of isotropic homogeneous turbulence everywhere, even where they may seem not to be applicable. And yet, somehow mysteriously, you see the emergence of Kolmogorov's 5k to the minus 5/3 law. So these are just some examples that I could actually think of to motivate why idealized models are worth pursuing, even in this complicated business of galaxy formation. So the idea is strip away non-essential complications and study the remaining very important things in great depth. So here is an image, HST image of a nearby galaxy. I think it's perhaps Whirlpool Galaxy, I don't know. The aim of theory is not to reproduce this image, right? If we just reproduce this image, we haven't really learned what goes on behind producing this image. But it is to understand the underlying processes which produce these amazing observations. So the best bet is actually to combine such idealized models with the complicated and more expensive models that I talked about previously. So, both the top-down and bottom-up approach of galaxy formation are very powerful. So I'll come to CGM observations now. As I mentioned already, the traditional focus of galaxy formation has been on stars, but they're highly nonlinear. So focusing on diffuse CGM, which is the source and sink of mass and energy to and from the galaxy, can be much more constraining, right? The reason focus has been on stars is mainly because we could not observe this diffuse phase earlier. Okay, so here is N-body. This is like a snap part of a cosmological dark matter only simulation. So these are galactic filaments, and at the intersection of these filaments you have these halos. So this is like a cluster halo, but at the intersection of smaller filaments you have things like groups and smaller mass galaxies like the Milky Way galaxy. Okay, so this is like a spherical cow model of the Milky Way. There is a spherical halo which is very big, and there are most of the stars are in a very tiny disk. There's a black hole at the center, which is also very, very important for galaxy formation. It is believed nowadays. This is the hot multi-phase plasma, which we call the circumgalactic medium. And the density of this gas is actually very low. So the CGM is typically unobservable in emission because emissivity goes like density squared. So if the density is low, you don't see much emission. But you can still perceive the presence of this CGM in absorption through quasar absorption line studies. In the intracluster medium, the circumgalactic medium in more massive halos, actually the gas is denser and it emits in X-rays. So the ICM has been studied in much great detail through X-ray telescopes like Chandra. So because you can actually make an image of the ICM is much better studied than CGM. So here are some clusters that I was mentioning. Here are some observations of clusters that I was actually referring to. So here you see an X-ray image of a massive cool core cluster, and you see these in magenta. You see, in magenta you see radio bubbles, which is displacing this X-ray gas, which is seen in blue here. So the intracluster medium emits X-rays because this plasma is at few times 10 to the 7 Kelvin and has a reasonably high density to emit profusely. So you can actually see these X-ray bubbles displacing the diffuse hot intracluster medium. The ICM not only emits in X-rays but also in cooler phases. In diagnostics which trace cooler phases. For example, these are filaments seen in the core of Perseus cluster. This is an H-alpha map. So you can actually see these filamentary H-alpha gas, which is almost like isotropically distributed. This scale is of order 40 kiloparsec. Not only this, some of these filaments also have CO. So this is an old CO map, which shows CO gas. So CO traces gas at less than 100 Kelvin, 10 Kelvin. This is 10 to the 4 Kelvin. And this is embedded within gas at 10 to the 7, 10 to the 8 Kelvin. So this is truly multi-phase. And you see it like in emission. Similarly, galactic outflows are also multi-phase. Here is the iconic image of Messier 82, a nearby starburst galaxy. So in green, you see the galactic stars. In blue, you see X-ray emission, which is sort of like hot X-ray outflow, which emerges from the center. It's driven by overlapping stars in the center. So there's a very high star formation rate density here. And these supernovae go off and power this galactic outflow. The red here is infrared. You can actually see dusty gas being thrown out in form of a galactic outflow. So there is hot gas, and there is like on the envelope of it, you see cold gas actually. So this is multi-phase circumgalactic medium again. But remember, the scale here is much smaller of the size of the galaxy. So this is much smaller than hundreds of kiloparsecs. Sorry, this should not be parsec. This is kpc, the typo. So this is still 20 kpc, much smaller than 200 kpc. This is a recent example of a galactic outflow, which is even much bigger than this. So this is an O2 map of a galactic outflow. You can actually see almost a similar morphology. There is an hourglass-like morphology where you have lack of O2 in the middle, and you have this is shaped by galactic outflow. So this multi-phase in O2 also traces 10 to the 4 Kelvin gas. So this is the CGM, which is supposed to be at 10 to the 6, and you have gas which is at 10 to the 4 Kelvin. The size here is 100 kpc, much bigger than this 20 kpc size. So this is one of the largest galactic outflows in the nearby universe. Similarly, you see high velocity clouds, or HVC, in neutral hydrogen. This is a galactic coordinates map of these different high velocity clouds. And some of these clouds are obviously associated with satellite galaxies like the LMC and the SMC, but a lot of them are, some of them are actually accreting low metallicity gas from the nearby IGM. So this is also part of the CGM, because this is within the halo of our galaxy. And this is 21 centimeter gas, so it's less than of order 1000 Kelvin, so it's not ionized. But they have been probed by other tracers, and they are sometimes surrounded by ionized gas. So this is for our own Milky Way. What about at even higher redshift? So imaging. So this is all here. I'm actually giving examples of emission probes. So here is an example of what is possible at redshift greater than 2. So here you see that these type of studies are only possible because of integral field spectroscopy. So these are integral field spectroscopy units at VLT, like MUSE, and at Keck, which is Keck Cosmic Web Imager. So here you are imaging high redshift universe using Lyman alpha transition in emission. So you see, so here these bright foreground galaxies are removed. So this is Hubble ultra deep field, and MUSE is looking at this field, and it sees H alpha bubbles almost fully covering the sky. So these are associated with galaxies in this field, and these very bright foreground galaxies are actually removed. So the understanding is that the CGM actually emits Lyman alpha emission on the scale of the circumgalactic medium. More detailed study shows like this is spread out over a scale of up to 50 kiloparsec. Now again, what's possible with these images like MUSE and KCW is shown here. Here you see a filamentary protocluster that's forming. So here you don't not only have an image, you also have the velocity information. So here, using the velocity and imaging capabilities, the authors have actually mapped out these filamentary structure in a protocluster. So you can actually see this is of order a megaparsec. So this is like a filaments sort of feeding a protocluster. So these were the examples of probes of the circumgalactic medium in emission. Going even at very high redshift. Of course, the resolution at high redshift is not as exquisite as in M82, for example, but you have a lot of, you cover larger scales, okay, because you can see much bigger area. Now the CGM is best studied, the nearby CGM is best studied in absorption because the density of the CGM is low. So since the CGM is dilute, it's hard to see it in emission. So Ashwin, how am I doing on time?
Hello, can you hear me? Yeah.
How am I doing on time? How much time do I have?
I think we started a little late. Maybe we could at about 3:20ish, 3:20, 3:25ish, because we should. Maybe we could extend for 5 more minutes beyond the time, I guess.
So how much time do I have?
You could continue for about 15 minutes, at least, I guess.
Okay. Okay. So this is a toy example of how this is an artist impression of how you can study the CGM in absorption. So this is a Hubble Space Telescope Cosmic Origin Spectrograph. There's a background quasar. Light from the quasar passes through the halo of a galaxy, and the spectrum of quasar gets etched by these absorption features from the CGM. So by studying these absorption features, we can actually study the properties of the circumgalactic medium in absorption. But to study the circumgalactic medium in the nearby universe, which is redshift of 0, UV spectroscopy is necessary. So that's why HST cos is a big thing in this field, because you can do UV spectra from space. But the MUSE and so on, being ground-based, can do redshift greater than 2 because the important UV lines such as line 1 alpha get redshifted to optical. So UV is very important for studying the nearby universe. So here is an actual example of this technique. So I'm actually not going to go in detail because I'm sort of running short of time. So this is like a true example of how that is done. And there are a lot of surveys based on this Hubble Space Telescope cross spectrograph. And so this is actually from the review of Tomlinson et al. It shows temperature density plot, and these different squares indicate the various ions that probe this particular density and temperature. For example, oxygen 6 probes temperature around 10 to the 5.5 and density around 10 to the minus 4. Okay, so and so on. So you have low ions which are probing predominantly the neutral gas, and then you have high ions like oxygen 8 which are probing the hot phase. So and what you see is a lot of these circumgalactic media show the full range of these tracers in absorption. Okay, now this is actually the reason, this inset shows the reason why you have to go to space and do UV spectroscopy, because all these lines are marked here as a function of redshift or the look back time. So redshift is what we care about. So most of these lines are actually in UV. So you have to go to space in order to observe them in the nearby universe. Whereas if you go to redshift beyond 2, a lot of these become accessible from ground-based facilities like MUSE. Okay, so a lot of the breakthrough was because of HST costs. So what are the key questions? So since you see such a range of densities and temperatures, the question is, how do you get this multi-phase gas in the circumgalactic medium? And what sustains this cold gas? Having this at a given time is not enough. You have to sustain it. So here is where the cloud crushing problem comes. I'll actually describe the setup. So the point is, once you have cold gas, it moves relative to the hot diffuse CGM because of gravity or because it is being thrown out or lifted up by outflows. So it is very common to find dense gas moving relative to the diffuse hot gas. So the cloud crushing problem is actually very related to a classic flow past a cylinder problem that some of us are familiar with. Here is like upstream conditions, and there is a barrier here, and there is flow around this barrier. So this is like a rigid barrier, a cylinder, for example. So as you increase the Reynolds number, there is a boundary layer formed, and it becomes turbulent if the Reynolds number is big enough. So we will actually be studying the cloud crushing problem, which is sort of like this. Of course, it's studied typically in the incompressible limit, but if you allow for compressible effects, you get something like this. So you have a headwind and there's a bow shock formed, and very similar phenomena of a turbulent tail occurs. And the Reynolds number in astrophysics are high because the system size is so big and the velocities are also big. Okay, so the difference of the astrophysical problem that I'm going to talk about from this physics problem that we have studied in fluid dynamics of incompressible flow past a cylinder is that this cloud is dense material, but it can mix with the wind. So it's sort of like high density stuff which is encountering low density wind, but it's not rigid, and it is allowed to mix into the wind that's coming from the upstream direction. It can mix in it, and it can also be moved by the wind. So typically the experimental setups for this flow past a cylinder, keeps the cylinder fixed at place, but they are actually quite similar. Okay, so there are, so this is the thing that I'm actually going to concentrate on for for most of, this is the crux of my bulk of my talk. So let me actually walk through the cloud crushing problem a little slowly. So what you have is a setup where you have an upstream wind, which is encountering a cloud. So the cloud has a density which is higher than the wind, has a radius RCL, the wind has a velocity V wind relative to the cloud. So, and these two gases are in pressure balance initially. So density of the wind times the temperature of the wind is equal to the density of the cloud times the temperature of the cloud. So we define a density contrast chi, which is just the density ratio of the cloud and the wind, which I sort of also integrate by hot, because the wind is dilute and hot. So since these are in pressure balance, rho CL times TCL is equal to rho hot times T hot. And we can actually define a Mach number for this problem, which is the ratio of this wind velocity to the sound speed in the hot medium, in the wind. The crossing time is just the time that it takes for this wind to cross the cloud. So this is just RCL by V wind. We can even express it in terms of the Mach number. So this is actually very, very important time scale, TCC, the cloud crushing time. So this is just chi to the 1/2, so the density ratio to the 1/2 times the crossing time. This is the time scale for Kelvin-Helmholtz instabilities to develop at this interface where there is a large shear. Right? These Kelvin-Helmholtz instabilities cause the mixing of this cloud into the hot wind. So this is also the time scale on which the cloud gets mixed in with the hot wind. The other interesting time is the drag time scale. This is the time over which the hot wind gets pushed appreciably because of this headwind. But what you notice is that this time scale has chi to the 1/2 scaling and this has chi scaling. And chi typically is 100, because you imagine this to be 10 to the 4 Kelvin in a CGM context, and you imagine this to be 10 to the 6 Kelvin. So typical value of chi is like 100. So the drag time scale is like a factor of 10, square root of chi, times longer than the time scale, the cloud crushing time scale, which is the time scale over which the cloud gets mixed in the hot wind. So this is actually the puzzle. The cloud is expected to mix before it can be pushed significantly by the wind. So this is actually a problem which is also called entrainment in trouble problem, and cloud pushing problem, and so on. So this is actually an important problem, because you see these galactic outflows where cold infrared traced gas is coming out. And the point is, if it is pushed by the hot gas, it should really not be pushed significantly before it can be mixed because of this Kelvin-Helmholtz instability. So this is actually a very important problem. Now, so this is this is actually the setup where you only have this shear between the cloud and the wind, and there is no cooling. We don't allow radiative cooling. Now things change fundamentally if we let gas to cool in this setup. So as the wind and cloud material is mixed, it produces gas at intermediate temperatures between the temperature of the cloud, which is 10 to the 4 Kelvin, and the temperature of wind, let's take that to be 10 to the 6 Kelvin. And that intermediate temperature gas has a short cooling time. So this is like a cooling function. Just to remind you guys, I'm actually assuming that the audience is all astrophysicists. So this is a cooling function as a function of temperature. So you see this is 10 to the 6 Kelvin. So let's concentrate on this line, which is for solar metallicity. So this gas is 10 to the 6 Kelvin. This is the ambient gas in the CGM or in a galactic outflow. This is 10 to the 4 Kelvin, which is the cloud temperature. And you see intermediate between the two, the cooling is very, very efficient. The cooling function peaks at 10 to the 5 Kelvin. So this has implications for this mixed gas that I mentioned will be created. So the gas which is produced in this mixing layer of cloud crushing has a very short cooling time. And including the cooling of that gas can have very important effect. So So let me come back to where I was. So these are some important diagnostics. So by the way, this work on cloud crushing was done by, along with my two PhD students, Vijit Khanjilal and Alankar Datta. And I think they are perhaps in the audience. So these are actually two important diagnostics. So what this plot shows, you will actually see this plot again and again. So it's better, it's good to understand it once. So this is the mass in the dense phase, right? So the cloud is dense and the wind is hot but low density, right? So what I'm plotting here is the mass in the fluid elements which have density greater than 1/3 of the initial cloud density, right? So if cloud and wind did not interact at all, this would be 1. This would go like this, right? 10 to the 0. But because of this interaction between the cloud and the wind, if there is no cooling, for example, I said that the cloud gets destroyed in a cloud crushing time. So what you expect is that a lot of this cloud surface gets eaten up, and the dense mass, the mass in the grid volumes which have density greater than the initial cloud velocity by 3 should fall down like this, right? So these dotted lines are simulations where we don't include radiative cooling. So what you see is that the dense cloud slowly gets smaller and smaller, and it just sort of plummets to 0 after a few cloud crushing times. So this is in the units of cloud crushing time. So after 3 or 4 cloud crushing times, all the cold gas, all the dense gas just gets mixed in the hot phase. Now that, what happens, let's see what happens if you include cooling. Now all these lines, you don't have to actually read the legend. All these lines are various combinations of this cloud density ratio, the Mach number, and the cloud size. And what you see is that some of these runs still show this destruction of the cloud, but some of these clouds show a very interesting regime where the dense gas falls initially, but then starts growing later on. So what is happening here is that there is turbulent mixing happening, but because the turbulent mixed gas has a short cooling time, it entrains gas from the hot phase and mixes it, brings it to intermediate temperatures, and this intermediate temperature gas cools and gives rise to this increase in the dense gas at late times. So there is a qualitative difference in simulations without cooling or with weak cooling, and in simulations where you have cooling which can be interesting. So the summary of this plot is that large clouds grow eventually if there is cooling present. Small clouds, or in absence of cooling, the clouds get mixed in the hot wind. So, and this is very, very fundamental, because if these clouds that we are talking about here are these clouds embedded in the circumgalactic medium, like the high velocity clouds, if these high velocity clouds are big enough, instead of getting destroyed by Kelvin-Helmholtz instability, they can actually grow. And this changes the whole sort of theoretical understanding of how you can interpret such multi-phase gas in the CGM. So this is, so this is dense mass as a function of time, and time is in units of cloud crushing time. Okay, and the takeaway is just this, by two types of different behavior. So these are the various parameters of our problem: NCL, the density of the cloud; TCL, temperature of the cloud. So for everything that I'll be talking about, these are fixed to 0.1 particles per cc and cloud temperature of 10 to the 4 Kelvin. And these are relevant for the circumgalactic medium. But we vary this density contrast, Mach number, and the cloud radius, and study these in numerical simulations. Now this plot shows the difference in velocity between the cloud material and the wind material as a function of time. This has the same runs which are shown here in the left plot, and you see that the behavior is more or less the same for all these runs, whether the cold gas grows at late times or whether it is destroyed at late times. So basically what this means is that the momentum transport between the hot wind and the cold cloud does not depend on the cooling physics. You know, whether you add cooling or do not have cooling, this is more or less the same. So here I'll actually show a simulation slide. So this is a cut of a simulation of our cloud crushing simulation. I'll play it again. What you see is the initial cloud and the headwind, and so let me play it again. So you can actually see the cloud getting shredded and disrupted by this headwind, and you can actually also see that initially, let me pause it, right? So so let's pause it here. So you see the spherical cloud has actually been, disrupted into a mess of mixed material, right? This is intermediate density between the ambient density and the cloud density that we have. And this also has intermediate temperatures. And recall that this intermediate temperature gas has a short cooling time. So this is at about 4 cloud crushing time. So here at this time, the cloud is actually being destroyed. But you will see as I play the movie, the cloud is almost, appears like it's almost destroyed. But see now, suddenly the cloud starts to sort of condense out of this mixed material that's sort of filling almost the whole volume. Okay. So this is what I was actually talking about. So this mixed gas cooling at late times is what gives rise to that late time rise in the dense gas mass that I talked about in the previous slide. So here are some of our parameters. So I talked about the physical parameters, which was just the chi, Mach number, cloud size, cloud density, cloud temperature. But the simulation parameters are also very important. So the important simulation parameters are the box size. So in units of the cloud radius. So here, in this case, the box size was 30 cloud radius in the X direction and 15 cloud radius in the Y and the Z direction. Okay, and this is a very high resolution run. So this is another numerically important parameter, RCL by D cell, which was 64. We are using the Pluto hydrodynamics code to solve this, and we are actually solving these equations in a frame which moves with the cloud material. This is actually very important because if you don't track the cloud material, the mixed gas very quickly leaves the computational box, and we are not able to simulate it for very long. We are using a cooling function for solar metallicity, and we turn off cooling below 10 to the 4 Kelvin. So this is our setup. I already talked about the cooling function, so I'll not spend time on this again. Here is actually a volume rendering. So what I'll show is like a volume rendering movie of this cloud at a fixed time, at late times. And what you are seeing is the cooling time. So cooling time is shown here, and you are sort of moving around this cold tail at late times of 14 cloud crushing time. So this is actually very computationally intensive, and we are grateful to SERC at IISc for these wonderful computational resources, and also the NVIDIA team, which helped us do these. In fact, not us, it really is done by Alankar mainly, and the simulations are produced by Vijay. So I am really just showing the results. So these are actually, this is a, you're sort of going, so the time is fixed, and you're sort of going through this tail of this multi-phase gas, seeing different cooling time. So the color represents the cooling time. So let me actually play it and pause it maybe. Yes. So this is the head of that cloudy thing, and you actually see this spaghetti-like structure. So right, so this has the blue has a low cooling time. So the material which has low cooling time sort of falls on this filamentary tail. This is red, so it has a longish cooling time. So anyway, I'll just let you enjoy the movie. So, and this shows a transparency. So what you are actually seeing is that the hot wind is transparent, and you're only seeing this mixed intermediate temperature gas with very short cooling time. Let me just let you enjoy this movie at a given time. So you're sort of going through this tail of filamentary cold material, and you see this spaghetti-like structure. Okay, so you are now again, just sort of going around it, and you actually see this is very, very fluffy and very, has holes and very, very turbulent, very cloud-like. Okay. Now, so movies are one part, but why are we so why? So this is not the first time that we have mentioned that you have this regime where cooling of the mixed gas can give interesting results. In fact, in 2018, these gentlemen, Max Gronke and Peng O, pointed this out that if the cooling time of the mixed gas and the cloud crushing time, the ratio of these two is less than 1, then you can actually explain this growth of cold gas and dense gas at late times. And this little more complicated looking formula can be converted into a radius. And this is the Gronke radius, which for typical numbers is about 2 parsec. So what it means is that for the typical conditions of the circumgalactic medium, clouds which are bigger than 2 parsec will entrain material from the hot gas around it rather than being destroyed by the hot gas. So this is in the regime where cooling happens. So clouds which are bigger than this will grow eventually. And this is actually not a very big size compared to the CGM size scales. So, this may play a role in, sustaining cold gas in the circumgalactic medium. Now, the problem is that other groups have questioned this. But I have to admit that our simulations are actually consistent with theirs. So by other groups, I mean, this result by Lee et al., they say that it's the hot gas cooling time, the cooling time of the hot diffuse gas of the wind material, rather than the mixed gas cooling time, which is important for growth of cold clouds. And they have a slightly different criterion, which is based on the cooling time of the hot phase. And if you convert this into a radius, this turns out to be this. And you can actually see the dependencies are very, very different. And even more importantly, the radius is actually like more than a factor of 10 higher, about a factor of 10 higher for these guys. So they're so there's a mystery here, right? Both criteria are based on similar numerical simulations. How can one group see growth whereas the other sees destruction of the cloud for the same parameters? It's actually almost like a Sherlock Holmes mystery. And what we did, so the key thing about Vijit's and Alankar's work is actually trying to get to the bottom of this mystery. And what can be the possible reasons for this discrepancy for the criterion of cloud growth? It can be the box size. So a lot of this is actually computational reasons. You can have a small box size, you can have different grid resolution, you can run your simulations for a different time. And actually what emerges out to be very, very important is what is actually meant by cloud being destroyed or cloud growing. Okay, so here is actually what I show here. Okay, what I show here is this the predicted lifetime of clouds, which is a generalization of this cloud crushing time, and my x-axis is the hot gas cooling time. So this dashed line is the Lee criterion. So if you're above this, your clouds should grow according to Lee et al. And if you're below this, your cloud should not grow. And we have actually in dark lines, we have actually marked the Gronke criterion. So you can actually see that they are actually quite different from each other. And what we have done is we have actually populated this space between the two, and the triangles in our simulations represent cloud growth. So we clearly do not agree with the Lee threshold. We agree with the Gronke threshold. In fact, there also we have slight differences, but this can be because of differences in our computational resolution may not be high enough. But the point is, intermediate cloud sizes actually grow rather than be destroyed. So we are actually consistent with Gronke-O rather than Lee. So we introduce this beta parameter here. So when beta is equal to 0, the cloud radius is the Gronke-O cloud radius. So when beta is 0, RCL is RGO. And when beta is 1, R is equal to R Lee. So, you know, when we do these simulations, these go from beta of 0.3 to beta of 0.8. And above beta of 0.5, we find cloud growth. So basically what we are saying is that we find cloud growth even for clouds which are significantly smaller than the Lee criterion or the Lee radius. So you know, now we are actually looking at these various effects that I mentioned. For example, the effect of box size. So here it's the same plot that I showed previously, the plot of dense mass as a function of time. What I have changed here is just the so here everything is fixed. So the box size is 20, 10, 10, which is much smaller than our box sizes. But what I'm doing is I'm sort of changing my beta. You can see the beta is different for these simulations. So I'm running it for beta of 0.5, 0.55, 0.6, 0.7. Well, here we are actually trying to see the effect of the box size. What we find is that, so in the previous case, we found that our beta of 0.6 simulations were giving cloud growth. So these have a box size of 400, 30, 30. These simulations have a box size of 20, 10, 10. So these are much smaller boxes. And what we see is with smaller boxes, with the same resolution as in the previous plot, we see that beta of 0.55 and beta of 0.5 show cloud destruction at late times and no growth. So there is, so what it means is that indeed a small box size reduces cloud growth because the mixed gas moves out of the computational domain. But this is not enough to explain the discrepancy. You know, you're changing the cloud size from 400 to 20 and the beta just changes from 0.5 to 0.6. It's not a big enough change in the cloud's radius to explain the effect that we are seeing. Now we look at the effect of resolution and box size. What is shown here it's the same plot. What I'm showing is increasing resolution from this blue to orange to green. As you increase the resolution, this dip in the dense mass is deeper and deeper. Okay, but you recover faster even though the dip is deeper. This dip is deeper because the turbulence is much more developed if your resolution is high. Now, these three are for our typical box sizes, which is 400, 30, 30. If we use this, if you do the same exercise for a small box, what we find is that this dips even below 0.1. Okay, and this dip is very is below 0.1, and this number 0.1 is actually important because Lee et al. Declare the clouds to be destroyed if this dense fraction falls below 0.1. So if this, for this simulation, Lee et al. Would say that this cloud is destroyed because this falls below 0.1. But you can see that actually this 0.1 is a very arbitrary definition. Okay, and we see growth just as it crosses 0.1. And in fact, Lee et al.'s box size is even smaller than this. So we think that it's the combination of high resolution. For high resolution, these dips are deeper. It's the combination of high resolution, small box sizes, and this definition of cloud destruction. That is, as soon as this crosses 0.1, you say the cloud is destroyed and you stop your simulation. A combination of these three factors actually gives rise to this wrong conclusion that cloud growth happens only for very big radii. If you relax even one of these, you would not see cloud growth for this case. So it's actually a very, the mystery was actually quite deep because it's three factors which cause this discrepancy. And in fact, the water gets muddier because last week there was a paper which says that they agree with the Lee et al. Criterion. So I'm quoting, we find that the hot wind cooling time sets the transition radius and not the cooling time of the mixed phase. I'm actually saying exactly the opposite. I'm saying it's the cooling time of the mixed phase which is more important in setting this physics than the cooling time of the hot phase, right? So these authors use a bigger box and are like us, and they also use similar grid resolution as us, but they still they agree with Lee et al. And this is actually very, very difficult to understand. Now, the issue is that how do we define cloud growth and destruction? Okay, so here are some plots from their simulation. This again is the same plot that I have showed again and again. So this is dense gas mass as a function of time. So you see growth here, but the most interesting lines are these. What they are doing is they are measuring at 12.5 TCC whether the cold or the dense gas increases or not, and declare that they see growth or destruction. So, but for one of their runs, in fact, for high Mach number runs, they are measuring this same thing at a later time. So the reason for this discrepancy is that the definition of whether you see growth or destruction should be robust and independent of who simulates it. And this is where the problem lies. So you can actually see, so they are using a time of 12.5 TCC for determining whether growth happens or not. And here in some of our simulations, we see growth even after 20 TCC, right? Here, the cold mass is decreasing, and only after 20 you will see it rise. So these guys would say that this is destroyed, but we would say that no, it's growing. So it's, the definition of growth versus destruction is very, very important. So we also propose a robust definition, and the definition is actually simple. You just run your simulation till the cooling time of the hot phase, which can be many, many TCC for large chi and Mach number. And you see whether by this time you see dense mass growth or not. If you don't see dense mass growth, then you can actually say that you cannot, you see cloud destruction in the tail. Because, and this time is a good time scale because you're focusing on the cooling of the turbulent mixed boundary layer and not the background hot phase. So I'm actually done with my talk. I'll just take 2 minutes. So one important question is, this cloud crushing stuff is quite interesting. But what it bypasses is, where does the cold clouds, where do these cold clouds come in the first place? So I have, my group has worked on this question in past, and we, for example, come up with a criterion for condensation of cold gas from the hot ICM, intracluster medium, or the CGM. If the background ratio of cooling time to the free fall time is less than something around 10, you get multi-phase condensation. Prakriti, who was a student working with me, has actually extended these studies to include large density fluctuations. So the x-axis here is density perturbation amplitude. So what you see is that above this sort of threshold, you see condensation from the hot phase. Below this, you see you don't see any condensation. So if your density perturbations are large, you can actually get multi-phase condensation even for longer cooling time of the hot phase. Anyway, this is not the main topic of the talk. Similarly, Aditi has worked on the origin of these multi-phase, these dense, cold dense clouds in galactic outflows in her simulation. So in her case, what she finds is that if you have supernovae which are spread over the interstellar medium disk, you can have the portions of the ISM being thrown into this galactic outflow because of this drag, because of the hot outflow. So these two are two plausible ways in which you can get entrained cold gas to begin with. So this is the question of the origin of cold gas to begin with. So these are my concluding thoughts. So I hope I have convinced you that these idealized setups are very powerful to discover emergent properties like the threshold T-cool mix by TCC and T-cool by TFF in the context of condensation from the hot CGM. Such idealized simulations are very powerful and help interpreting complex simulations and observations. CGMs are great because we can study them through so many observational probes. I only talked about a handful. There are many more, like Sunyaev-Zeldovich effect and the fast radio bursts and so on. I focus on the cloud crushing problem. This is prototype of multi-phase gas in the CGM. I did not focus much on the physics, but just about the discrepancy between some recent results. There's a lot of physics going on, and we have actually highlighted it in our recently submitted paper. You should check it out on archive, which will appear. It will hopefully appear in a few days. And then I actually briefly mentioned about where do you get the cold gas in the first place. Now, the question that I did not answer at all was, once your cloud starts to grow, it cannot grow indefinitely and eat up all the hot phase. It has to grow, it has to stop growing at some point. And that physics people haven't really yet explored. So that's another thing that I'm actually trying to look at with my group. Thank you for your attention, and sorry for exceeding the time.
Thank you, Prateek. Thanks for pointing out the subtle distinctions between the results that have come out from different groups, which have been very puzzling, really.
Yes, I thought since it's an astro audience, I would go a little bit in detail. Sorry,
yes. So is there any questions, comments?
Oh, Kambu is also, yeah. So I'll
Any
question?
Saurabh has a question.
I had a question, Prateek. This is Naren here.
Go ahead.
Yeah, Naren, please.
Yeah. So in the first part where you mentioned that, okay, I mean, there will be some size below which the cloud will be destroyed.
Yes.
So does it mean that observationally we expect to find, like, if I plot a size distribution, for example, of the clouds,
yes,
observationally, so do I expect there would be a cutoff?
I think so. You do not expect a lot of big. You do not expect a lot of small clouds. They are evaporated very, very quickly. At least within the context of this this setup, small clouds are destroyed because of evaporation by the diffuse medium. Yes,
right.
The small clouds will be evaporated. But the reality can be very, very complicated. You have to worry about the background thermodynamics as well. But the other thing to remember is that the sizes are actually quite small. Tens of parsec that we're talking about, right? So I don't know if such small.
Yeah, it would be hard to.
Yes.
Okay.
Yeah.
Suchetana?
Yeah.
Oh, hello. I just have a very simple question. So if you go to the end of your, so Prateek, since these are first of all, this is a fantastic talk. And do you have any plans to, I understand that these are idealized simulations, but do you have any plan or proposal to sort of do any kind of comparison with observations, like real observations?
So see, observational comparisons I have actually done a lot in the intercluster medium context, which is where I have more background. But this stuff also, things like 21 centimeter H alpha and so on, one can actually do that. I've actually collaborated a little bit with the cosmological hydrodynamic simulators recently, and we do similar, we try to interpret what they find in similar terms. So yes, I mean, that's where the most interesting outcomes are produced, right? When you do a cross fertilization between.
That's right. No, I was talking about because there are these CGM observations coming out of these outflows. So if you and your group you can design something so that some kind of direct observations, and as you said that you are collaborating with the cosmological simulation group, that would be also nice, but I suspect your simulations will have much finer resolution. Certain things can be deduced from there. Thank you.
Yeah, absolutely. We are open to comparing with observations. But right now, what the state of theory and simulations is actually rather primordial. So even the existing observations are quite difficult to explain. So that provides us sufficient puzzles to solve.
Yeah.
Even that is good enough for now. Yeah.
Kandu?
Hey Prateek, very nice to see these results. I heard actually Pengo talk about it few years back. Your cloud, I mean, just a small comment, your cloud looks like coronavirus.
Oh, what looks like?
But more seriously, there are two issues, physics issues. One is viscosity.
Oh, the cloud looks like coronavirus. Okay. Okay.
So viscosity in the hot phase, the density is low and the temperature is high. And the viscosity coefficient goes pretty steeply with temperature at least.
Yes. What you're saying is absolutely right, that the mean free path in the hot gas can be pretty long. But I am relying on magnetic fields. See, if you recall, my thesis was actually...
Yes, absolutely. Correct.
So I studied a lot of collisionless effects and so on. And, in the end, spending those many years on that, what I concluded is magnetic fields imposes a lot of collisional-like behavior on a plasma. Of course, that may be totally wrong, but from the kind of things that have come out till now, it appears that using like a enhanced viscosity, it may not be a bad approximation. But what you're saying is absolutely right, that the mean free path is so long that you have to worry about viscosity, at least formally.
Yes, of course, the magnetic field brings in the other complication, because both viscosity and the magnetic field draping around the clouds will suppress Kelvin-Helmholtz.
Absolutely. See, here we really wanted to get to the bottom of these quite different physical results. Now we are 2 versus 2, but I think it will quickly become 1 versus 0, because I think we have really gotten to the bottom of the reason for differences in these simulations. And that is
fantastic. Absolutely. Very nice.
The reason I'm spending such a long time on technical stuff, because the answer for that question is actually technical. The mystery is solved at a technical level in this case.
Yeah. Okay. I mean, very nice. I really liked these simulations that you have done. Thanks a lot, Prateek.
Thanks, Kandu.
Okay, Ritaban?
Hi, this is Ritaban. Can you hear me?
Yes, Ritaban, I can hear you.
Oh, so my question is actually related to one of the previous questions. So, the Gronke O radius, that is about 2 parsec.
Yes.
Now, I mean, the galactic molecular clouds are all mostly bigger than that size. So what is this? I mean, it seems to me that most clouds will be bigger than that.
That's correct.
So then most of them will not be destroyed, but they will sort of absorb and sort of grow.
Yes, so that's why this is good news for CGM observations. All CGM observations show multiphase gas. So what this means is that even if these clouds are, falling through the hot medium, and even if there is Kelvin-Helmholtz instability at the boundary layer, they do not get destroyed. So we don't, this was actually one of the big open things, like, oh, you have clouds, that's good, but what if it gets destroyed by Kelvin-Helmholtz instability? So people previously just compared the Kelvin-Helmholtz time scale with like a free fall time from that radius. That's not the right comparison. The right comparison is actually this. And you are actually growing rather than being destroyed. So, what it means is that you can very easily sustain multi-phase gas rather than get rid of it very, very quickly.
Okay, so that's what I was getting at, that observationally there is, I mean, broadly there is some matching with what we get in the observation.
That's very coarse-grained level, but at
Right,
a qualitative level.
Right.
But it's actually quite nice because, you know, the whole field was sort of had this niggling doubt whether this will work. You know, for example, I have worked on this condensation. Now, once you condense, these dense clouds fall in gravity, and people say, oh, they will be very quickly mixed by Kelvin-Helmholtz stability. Now, what this work says is no, it will not. It's very big. In fact, it will grow at the expense of the hot phase. So this actually is I think this is a very, very important result. And that's why, you know, we took the time and effort to really get into the bottom of this.
Okay, very nice. Thank you.
Yeah.
Naren, I
Yeah,
see you raise hand.
Yeah, Prateek, say for example, when you do this simulation, you must have the velocity field as well, right? So
let's go. Yes.
yeah.
Yes.
Example, I mean, CGM observation, absorption observations. So if I say, let's say I have like smaller clouds, 2 per second size, and I have larger clouds, like, you know, big clouds. So does it, like, you know, produces difference in the, you know, turbulent motions and velocity field, so that the absorption line, which you would expect to see, that will have different kind of RMS, or, you know, it will put some signature in that? Observationally, is it possible to?
Yes. See, the velocity signatures, you know, here is the momentum transport, which sort of reflects the velocity, right? You know, if the two phases are able to exchange momentum, you know, they will be co-moving, otherwise they'll not be. So the momentum exchange doesn't really get affected by cooling at all. So, you know, if the clouds are very, very small, they will get evaporated. You should not see very small clouds. In fact, the prediction of this is that if you see very small clouds, there is something wrong with, you know, at least this theory does not apply or explain that. So, but in terms of velocity, I don't see, you know, velocity differences being there. You know, there are differences just because the drag time scale is different for bigger clouds and smaller clouds, but you can actually scale them out. You know, the details are of course always messy. But, you know, these ideas actually definitely can be applied. In fact, if you have some observational handles on such, you know, probing such theoretical ideas,
Yeah.
I'd be very, very happy to discuss.
Yeah. Okay. See, for example, in this box, I mean, we already have this simulation box. So if I like shoot a line of sight, and can I predict that what I am expect to see in absorption, for example, like, you know,
Right.
density,
So for example, one can actually do like an absorption study or an emission study. So the step involved is actually going from density, temperature, velocity to NH1, and that's where, you know, a lot of uncertainties come in, right? So that's where I also don't have a lot of experience. So if you know, if I give you like density, temperature, velocity fields, can you, you know, convert it into absorption maps and, you know, 21 centimeter columns and so on?
Yeah, it should be possible.
Yes.
Yeah, I think, yeah.
In fact, we should talk about it. You know, these two students are just starting. You know, Alankar and Vijit both are just starting with their thesis. So they will have a lot of time. So if there are good problems related to this, they can actually look at it seriously.
Okay, so if there are no more questions,
All right. Yeah, sure.
Comments, let's thank Prateek again for this wonderful thought-provoking talk.
Yeah.